So if we have multiple multiple electrons, I think, then there will be multiple electrostatic force between them. So if multiple electron forces acting on a particle, the net force is the vector sum, not a scalar sum of the individual forces, which means that if altogether we have a small n charged particles, then on the first one, then which means that 2, 3, 4 up to n charged particles will have a force acting on charge 1, and 1, 3, 4, 5, 6 up to n will have force acting on charge 2. So they are all different. And of course, if you need to calculate the force acting on charge 1, then you need to add the force due to charge 2, 3, 4 up to n, and then you add them together with a vector sum, not the scalar sum. I suppose you should know how to add the vector. You decompose it in x-axis, y-axis, and then you add the x-axis components together and then y-axis component together to form the total vector. I think you should know how to do that. Okay, so this is the case when we need to solve for the system with multiple charges. And here we have the Shell theories. I think I could not tell you why at this moment, but yeah, I think in chapter 23 we will just come back to tell you why it will be like that. But here I just let you know what is this two Shell theorem is. So there are two Shell theories for the electrostatic force. The first one is a charged particle outside a shell with a charge uniform distributed on its surface is attracted or repelled as if the shell charge were concentrated as the particle at its center. So let me tell you what it is talking about. So if we have a shell, of course it is a 3D sphere, but yeah, I don't know how to draw a 3D one. Yeah, maybe I can draw a better one at least. This one. Yeah, I can draw a perfect circle here like this. Yeah. So if we have a sphere, and then it says charged particle outside a shell with a charge uniformly distributed. So this uniformly distributed is a keyword. It's important at this case. So if it is equally distributed, say like this. Suppose the total charge, we call it Q, maybe Q1, and then of course this is a sphere. Actually, this is a sphere, not a circle. No, okay. So yeah, of course a sphere should have a center, and then maybe we have another charge Q2 here, charge Q2 here. So for the Coulomb's law, you only know that if we have a charge Q1, Q2, then suppose they are all positive charge, then there will be Coulomb's force attracting them, right? Suppose they are a positive charge, plus Q1 plus Q2, like this. And the Shell theorem tells you that if the Q1 is equally distributed on this sphere, and then we have a Q1, then the force acting on this charge and the sphere are actually the same. You can regard all the charge are distributed at the center of the sphere. This is what Shell theory once said. We can try to recap it again. So a charged particle outside a shell with charge uniform distributed on its surface is attracted or repelled as if the shell charge were concentrated at the particle at the center. Okay, so this is Shell Theorem 1. Okay, so for the shell theory 2, a charged particle inside a shell with charge uniformly distributed on the surface has no net force acting on it due to the shell. Okay, so this case is like if you have also a shell like this, and then you also have charge uniformly distributed on the surface. So which is like like this, and then suppose you consider a charge placing inside, not necessarily the center, just inside the sphere. Maybe it is still Q1. Then there will be no force acting on this charge. It will feel strange. If it is at the center, it's clearly that all the force will cancel each other. But even though this charge is not at the center, but as much as it is inside the sphere, then all the force will cancel each other. You may simply imagine that maybe we can just this is the center. Maybe we can just connect this point, and then you can simply imagine the left side and the right side will cancel each other because not so obvious. But at least you can imagine that. For the part here, for the part here, the left side and right side will cancel each other because, for example, this part will generate a force pointing to this side. This part will generate a force pointing to that side. So the left side and right side will cancel each other. They will add up like this. So for this part, it will generate a force pointing to slightly bottom. And for this part, it will generate a force pointing to this side. And believe it or not, they will cancel each other perfectly. So this is difficult. If you really need to prove it using the calculus, this integration is not easy to calculate. And actually for Newton's, when he tried to discover the gravitational force, he also come up with a similar integration problem like this. And actually this is a Shell Theorem too. So it says the charged particle inside a shell with a charge uniformly distributed on the surface has no net force acting on it due to the shell. So suppose if you have a charge inside the shell, then if the charge is equally distributed, then there will be no force acting on Q2. And this is Shell Theorem 2. Okay. So here we have a quick checkpoint. It asks, the figure shows two protons, simple p. These two are protons. The one electron E on an axis. On the central proton, what is the direction of the force due to the electron? For the central proton, what is the force acting on this one due to the electron? Left or right? Left or right? Left. Oh, left. Because they have opposite charge, so they will attract each other. So for the B, the force due to the other proton. due to this one. Also left, right, so left, because they have the same polarity, so they repel each other. Okay, so the net force left, both are pointing to the left, so here, left. Okay, so this is simple. Okay, here we have a sample problem. So it says figure A shows two positively charged particles fixed in place on an x-axis. The charges are Q1 and Q2. And the particle separation is R, capital R. What are the magnitude and direction of the electrostatic force on particle 1 from particle 2? Okay, so both of them are positive charge, so they should repel each other. So F12, which means the force acting on Q1 due to Q2, so we call it F12, should point to the left side. Okay, so we can say, we can write it as F12 equals K times Q1, Q2 over R squared. This one is capital R, so I write capital R here. And originally we don't have the absolute value here, but actually you can just try to calculate the magnitude of the force, and then you just determine the direction of the vector by yourself. Is okay. So we just take the absolute value here, so make everything positive, and then yeah. So we just plug in the number. K is 8.99 times 10 to the 9th power, and then Q1 is this one, 1.6 times 10 to minus 19, and then sometimes later we will know this is the elementary charge, 1.6 times 10 to minus 19 Coulomb. And then Q2 is this one, 3.2 times 10 to minus 19, and then all over 0.02 square. Okay, so this is easy. We have a negative 1.15 times 10 to minus 24 Newton. And if we try to write it in a vector form, it is like F12 equals we don't have a negative sign here, it's positive. So actually this is x-axis, and actually x-axis should point to the right side. So in this case, if you try to write it in the vector form, it is like negative 1.15 times 10 to minus 24 Newton. And then we'll use this I hat, or sometimes I just skip this I. So I hat or I hat is the unit vector of x-axis, and then j hat or j hat is the unit vector of y-axis, and then k hat is the unit vector of z-axis. So in this textbook, it usually use I hat, j hat, k hat to stand for the unit vector for x, y, z axis. Some of the textbook may use x hat, y hat, z hat, or yeah, like that. But they stand for the same thing. But it's just some kinds of notation, so it will be fine. Okay, so this is the answer for part A. And then for the second one, yeah, C is identical to the previous one, except particle 3 now slide on the x-axis. Yeah, we have one additional charges between Q1 and Q2. And then Q3 is a negative 3.2 times 10 to minus 19. The distance between particle 1 and 3 is 3r over 4. What is the net electrostatic force on particle 1 due to particle 2 and 3? So just now we already have this. F12, the force on Q1 due to Q2, and then we also need to find Q1, Q3. So F13 is nothing but K times Q1, Q3, and here should be 3R over 4, 3R over 4 quantity squared. Okay, so we just plug in the values, 8.99 times 10 to the 9th power times Q1 is still 1.6 times 10 to minus 19, and then this one taking the absolute value, 3.2 times 10 to minus 19. Here we have the 3 times 0.02 all over 4 quantity squared. So when you try to use your calculator, you can find it as 2.05 times 10 to minus 19 Newton. And actually, this is positive, this is negative. F13 points to the positive side. So in this case, F13 vector is 2.05 times 10 to minus 24 Newton. And then I, like this. So F1 net should be F12 plus F13. Okay, so it should be like negative 1.15 times 10 to minus 24 Newton I plus 2.05 times 10 to minus 24 Newton I. So it turns out to be 9 times 10 to minus 25 Newton I. Okay, so this is the net force acting on Q1 when we have a Q3 here. So it is still simple. Okay, so the next case is if we place Q4 not actually on x-axis, some place here. Theta is 60 degree with x-axis. The distance between Q4 and Q1 is still 3R over 4. So we know F14 is nothing but 2.05 times 10 to minus 24, because the charge amount doesn't change, the distance doesn't change, so the force, the magnitude of the force doesn't change. Only the direction changes. Only the direction changes. So in this case, F14 is actually 2.05 times 10 to minus 24. So you need to decompose it over x-axis and y-axis. So this one is cosine 60 degree, cosine 60 degree, Newton I, and then plus, plus 2.05 times 10 to minus 24 times sine of 60 degree, Newton J, because this is y-axis, so this is J here, J hat here. Okay, so this is nothing but 1.025 times 10 to minus 24 Newton I plus 1.78 times 10 to minus 24 Newton J. Okay, so finally F1 net is F12 plus F14. Okay, so you can simply find that this is F12, this is F14. So along x-axis, we have this one subtracting this one. So the answer will be minus 1.25 times 10 to minus 25 Newton I plus 1.78 times 10 to minus 24 Newton J. Okay. Okay, I think you can still do it easily with the knowledge of a high school physics. Okay, so let's move on. Here it says figure A shows two particles fixed in a place. A particle of charge Q1 is AQ plus AQ at the origin, and a particle of Q2 negative 2Q at x equals L. At what point other than infinitely far away can a proton? We need to place the third one between so that it is in equilibrium. But actually, the false assumption is that Q1 and Q2 doesn't really move at all. But actually, that's not the case because there should be some force attracting them. There should be some force attracting them. So yeah, it's just assumption that these two particles are fixed there, and then you try to place a proton in between so that the proton doesn't move, which means that there will be no force acting on the proton. So there will be no acceleration on it and it doesn't move at all. Okay, so let's consider three cases because it asks you to place the proton on the x-axis. So there will be three regions. The one is on the left, and then the second one is in the middle, and the third one is on the right. So let's consider this one first. If we place this proton in the middle of Q1 and Q2, then Q1 and this proton are all positive, so they will repel each other, which means that F1 points to the right side. And the proton and this negative charge has opposite charges, so they will attract each other, which means that F2 also point to the right side. So both forces point to the right side, so they can never cancel each other, which means that this case is not this case is not possible. You can never place a proton in between so that the net force is zero. And next we consider a case on the left region. If we place this charge on the left region, F1 points to the left side. Okay, they are positive, so they repel each other. This one and this one, they have a negative charge. They have opposite charges, so they attract each other. So this force point to the right side. However, for this case, F1 always larger than F2 because you can simply imagine F equals K times QB over R squared. So for Q1 and the proton, Q1 has AQ. Q1 has AQ. Q2 only has 2Q, which means that for QAQB, this one is larger, is much larger, 4 times larger than Q2. And the distance between Q1 and the proton is much less than Q2 because this is the distance between Q1 and the proton. For the distance between Q2 and the proton, you at least need to add this part, which must be larger than this one. And this term is in the denominator, which means that the smaller the denominator is, the force will be larger. Then yeah, so you can imagine that F1 always is larger than F2. So in this case, F1, F2 cannot cancel each other either. So for the third case, if we place this proton on the right side, then you can imagine Q1 is larger than Q2, so that the numerator is larger for Q1. However, the distance between Q1 and the proton is larger than Q2. so that for Q1 the denominator is larger also, so that there may be the point that these two terms can cancel each other perfectly. So in that case, that we may try to solve for these cases. Okay, so here we have, so imagine this case, we have a K times 8Q and then QP. QP is the charge of the proton over, we assume this distance is x. This distance is x, so we have x squared here. It should be equal to K times 2Q times QP, and then all over. This one should be x minus L, because the distance between Q1 and Q2 is a capital L. So this is x minus L squared here. So actually we can do some simplification. K and K can be cancelled. QP and QP can be cancelled. Q and Q can also be cancelled. This one is 4. So you can just put this one over, put this one over. You can have you can finally get 3x squared minus 8xl plus 4l squared equals 0. And then you can find two solutions. Because it is a quadratic equation. You can have two solutions for it. So the first one is 2l over 3, and then the second one is 2l. So actually this one will be rejected. This one will be rejected. The reason is that if x is 2l over 3, which means that the charge will be here, which is not the case on the right side. Which is not on the right side. So we should reject this solution. The only solution should be this 2l. Should be this 2l. Which means that we should have a positive and then negative. This is Q1, Q2. This is L. This is also L. And then we place a proton here. This is 8Q, this is negative 2Q. Then this proton should have a 0 net charge. Okay, it also asks, is that equilibrium stable or unstable? This is a little bit tricky. Maybe I can try to explain it a bit, but yeah, it's not so easy to really understand. Actually, the answer is it will be unstable. It will be unstable. It will be unstable. You can actually try to derive something, then you can see why it will be unstable. So the simple derivation is like, just now we have the force. We have the force like this. So if we consider the net force acting on it, it will be like F net equals K times 8Q QP over x squared minus K, and then times 2Q QP x minus L squared, like this. I just try to move this one to the other side. Suppose x is not necessarily 2L. So I just move it over. So it is the net force. And then of course we can just factor out some common factor. K and then 2Q QP. So the remaining one will be 4 over x squared minus 1 over x minus L squared. Like this. So these one are all positive factor, we just try to ignore it. The point we consider is that to consider whether the proton is stable or unstable is like you try to push it a little bit right. If there is a force pushing it backward, then it will be stable. If the force is pushing it further to the right further, then it is unstable. It is like if you have curvature like this, and then you have a ball rolling here. Then if you try to push it to the left, then it will roll back. And if you try to push to the right, it will also try to roll back. Then this is considered as stable here. If you have a curvature like this, you spend much effort to try to put this ball here, and it doesn't really fall. But if you try to push it a bit to the left, then it will try to go. It will just fall down. Or if you just try to put this to the right side, it will fall down. Then this is unstable. This is unstable. So here we try to make x to be 2L plus a small delta L, and then we try to plug it here. Then we'll see this F net will be if we just consider this term, it will be like 4 over 2L plus delta L square minus 1 over 2L plus delta L minus L quantity square, like this. So we have 4 over 4L square plus 4L delta L plus delta L square minus this one is L plus delta L, so it will be L square plus 2L delta L plus delta L quantity square. And of course we assume this one is small. This one is small, so the second order term can be ignored. This term can be ignored, and it will be like approximately like 1 over L square plus L times delta L, and then minus 1 over L square plus 2L delta L. So you can see that this one is smaller for the denominator. This one is smaller than this one. So the whole term is positive. The whole term is positive, which means that if you try to push the proton a little bit to the right side, the force will be positive. So the force will push it to the right side. It makes it unstable. Okay. So yeah. So maybe we just stop here today. Next week we will just continue to finish off here.